All right, welcome back to class. I'm going to make sure I'm not on mute. I think I'm good. Anyway, there have been a few questions about the upcoming exam. The exam's scheduled for Saturday, anytime, all day Saturday through the end of the day. If you have accommodations through the UAC, you can, I will make sure that you're automatically given the time that you are expected to have and the flexibility on test dates that your accommodations give you. If you're in a situation with non-emergency considerations and you don't have formal accommodations, but you nevertheless would like to make a request, you can feel free to contact me and see whether arrangements can be made. Let's see, the exam is going to cover the parts of chapter 7 and 8. I believe, you know, for exam 2, we only really got through substitution. So the exam will include the stuff from 7 and 8 where you were required to think about substitution competing with elimination. It will also cover chapters 9, 10, and 11, though fortunately 11 is basically the same as 10 and we're not going to spend that much time on it. I had intended for the exam to cover chapter 12, but it will not because we won't have enough time before the exam. All right. And folks have asked questions. What do you typically see students struggle with at this point? I think the sheer amount of detail is overwhelming. And so I've encouraged people to look for themes and concepts that weave many of the reactions together. For example, in chapter 9, the theme was let's convert OH into a good leaving group, and then we can do the substitution and elimination reactions we're used to. And then in chapter 10, the theme has been pi electrons acting as nucleophile. And the key feature is whether or not you have a carbocationic intermediate. And if so, that carbocation needs to be on the more substituted carbon. Okay. There are requests about moving the exam, doing it on a weekday. As I said, I'm not going to change the date of the exam, but if you have a circumstance that would seem to justify a little bit of flexibility, you can contact me. All right. So today I wanted to show you an application of what we've been learning so far. And this will involve a class of natural products that are called terpenes. And the steroids that I showed you last week are terpenes, and they are synthesized and derived from this process. Terpenes have a basic 5-carbon unit that is based on the following diene. This molecule is called isoprene. You can polymerize it to form rubber-like polymers such as those that are used to make basketballs and so on. Terpenes have these 5 carbons linked together in a characteristic way. So I will number the carbons of this isoprene as 1, 2, and then I'll call this branching methyl group 3, 4, and 5. I realize in doing that, I am not numbering it in the IUPAC way, and I don't care. So we'll number the carbons of the isoprenes that way. Molecules that come from this kind of subunit, the squiggly line will indicate where this subunit is connected to other things. But you're going to be looking for a characteristic pattern of 5 carbons, 1, 2, 3, 4, and 5. And we'll call sort of this side of the isoprene unit the head, and this side we'll call the tail. And in general, isoprenes have terpenes have carbon 1 of one isoprene unit attached to carbon 5 of the other isoprene unit. So terpene that I think we talked about before was, let's see, dang it, the following molecule. And then I've abbreviated the pyrophosphate group before as follows. I will illustrate that one time here just for completeness. And I'll point out that that pyrophosphate group is almost always associated with a magnesium counterion. So it's a better leaving group than you would think with the 3 negative charges on it. I'll highlight here the two isoprene units that make up this molecule, Geranil Pyrophosphate. And I don't know why they call it Geranil, no idea, other than maybe because of it's a derivative of geraniol, which is like rose oil, and maybe you can get it from geraniums too. I have no idea. Here is one of the two isoprene units, 1, 2, 3, 4, and 5. Here is the bond between two of them. And then here is another one, 1, 2, 3, 4, and 5. There's some weird nomenclature with these kinds of things. If a molecule has two isoprene units, it is called a monoterpene. If it has 3 isoprene units, it would be called a sesquiterpene. That's weird. Sesqui, I think, is a prefix that means 1.5. If you've heard of sesquicentennial, I don't know. Back in 1986, I lived in Texas, and it was a big deal because that was the sesquicentennial of Texas's 1836 freedom from Mexico or something like that. But that's the only time I've ever heard it. 4 would be a diterpene, and so on. That's not particularly important. Someone on the chat is asking, is this stuff from chapter 11? No, this is stuff from science. It's not really in your textbook. So it just is. But it's based on principles from chapters 10 and 11. So it's useful when you're looking at terpene natural products to try to identify the individual isoprene units in them, because then you can think about how that product was synthesized. So before we talk about the chemistry that some of these molecules can do, I want to just show you a few terpene natural products, and then we'll work on identifying the isoprene units in them. So this natural product is called limonene, and it's in lemons. It's one of the things that gives citrus its characteristic smell. When you want to identify isoprene units in these natural products, you start by looking for the branching methyl groups, because that tells you which carbons are 2 and 3 in the isoprene unit. All right, so here is a branching methyl group. What do I mean by branching methyl group? Basically, I'm looking for tertiary carbons, right? I'm looking for a carbon that's bonded to 3 other carbons. And I know that if once I found that tertiary carbon bonded to a methyl group, that's carbons 2 and 3 of my isoprene unit. And then down here, I've got a tertiary carbon bonded to a methyl group. And so that would be carbons 2 and 3 of an isoprene unit. Okay. So based on what an isoprene unit looks like, let's start with the orange isoprene unit. Which of the carbons there should be carbon 1? Right, because remember, it's got to be 5 carbons. If you put 1 here, where would carbon 5 be? Yeah, so let's put 1 here with the double bond. Okay, that would make this one 4. And then we'd have to choose whether this one or this one is 5. And actually, it wouldn't much matter. And it would be difficult to tell. Let's just pick one direction and say this is 5. Okay. That would mean that this is a bond that connects 2 different isoprene units. And that would mean the other carbons come from the second isoprene unit, and we could number 1, 2, 3, 4, and 5. So those are the 2 isoprene units in limonene. One of the ways you can know that there are 2 isoprene units there is simply to count the carbons. There are 10 of them. And each isoprene unit has 5. So that's how you can tell how many isoprene units are in a natural product. Another thing that can be useful when looking at a isoprene or a terpene natural product is to distinguish between bonds that connected isoprene units in a linear precursor versus bonds that are new. So notice Geranil Pyrophosphate has these same subunits. It has 2 isoprene units linked together, and there's a bond between the 2 between 5 of one and 1 of the other. And similarly, as we've identified down here, those isoprene units, this red bond was in the linear precursor. And that way we can look and say, okay, well, if that's true, then the new bond we would have had to form in this process, this bond between 4 of one subunit and 5 of the other, this is a new bond we would have to have made. And I guess I'm getting a little bit ahead of myself because there is a very straightforward process using reactions that we know that converts geranil pyrophosphate into limonene. And this is how lemons and limes and citrus make that particular molecule. All right, so your principles in finding an isoprene unit in natural products are, first, look for the branching methyl groups. Second, ignore pi bonds and oxygens if there are any. And then look for the head to tail sigma bond between carbon 5 and carbon 1 that was in the linear precursor. All right. And we'll see some other kinds of examples later, and we'll have a little bit more practice on this. So let's talk about what kind of chemistry these natural products can do. So starting with the first sort of reaction is leaving group leaves. That is the first step of the SN1/E1 reaction. And this is boring, but you can understand why it happens. I'm going to, again, identify the 2 isoprene units in this molecule. And we're going to notice that the pyrophosphate group attached to carbon 5, oops, confused myself. The pyrophosphate group attached to carbon 5 is at an allyl carbon. Remember how we sometimes talk about olefins. The carbons that are involved in the double bonds are called vinyl carbons, and the ones adjacent to that are called allyl carbons. And whenever you have a leaving group at an allyl carbon, that needs to be a situation where you think, okay, even though that carbon's only a primary carbon, probably SN1 and E1 are possible, because if that leaving group leaves, then the positive charge is on that allyl carbon where it is stabilized by resonance. So here is the carbocation that is left behind once the leaving group leaves. Okay, there's the sigma bond between carbon 5 of one isoprene unit and carbon 1 of another. And notice that that positive charge is not just a primary carbocation, it's resonance stabilized. And that's why this first step can happen. You can delocalize that positive charge on the tertiary carbon as well. All right, so that's one simple reaction that terpenes can do. Why would you want to do this? Well, this generates a reactive intermediate that you can then do other types of chemistry with. The second type of reaction that we can get in terpene chemistry is pi bond acts as a nucleophile, attacks a positively charged carbon, a carbocation, or in other words, an empty p orbital. Okay, so let's redraw this carbocationic intermediate from Geranil Pyrophosphate. And I'm going to draw it in a way that will start to resemble the shape of the limonene molecule. Oops. All right. So I'm going to put the two methyl groups on the head of my carbocation, the orange methyl groups. I'm going to put them here. And then here's going to be the bond between 5 and 1. 1, 2, 3, 4, and 5. And then 1, 2, 3, 4, and 5. And we're going to remind ourselves that that positive charge is delocalized not only on the tertiary carbon, but on the primary carbon. And so we can draw a resonance structure where that positive charge is on carbon 5 of my blue isoprene unit. Okay. So all I've done to get from here to here is I've just rotated around this bond between carbons 5 and 1. All right. Any questions or concerns about how we got there? Okay. Sorry. I wanted to draw the bonds in black and then I wanted to highlight them. So sorry about that. I have to redo my drawing. 1, 2, 3, 4, and 5. Now, I said before we had to somehow account for the formation of this bond between carbon 4 on one isoprene unit and carbon 5 on the other. So it turns out that we're perfectly set up for that just based on the connectivity of this molecule. you have carbon 5, blue carbon 5 with a positive charge on it, and it's pretty close to orange carbon 4 that's involved in a pi bond. Okay. So now we're going to use principles from chapter 10. Pi electrons act as nucleophile to attack an empty orbital on carbon. Sorry, I'm missing a double bond there. That's going to create a new sigma bond. Now, there are two carbons in that pi bond, carbon 2 and carbon 4. Which one gets the new sigma bond and which one gets the positive charge, and why? You want carbon 2 to have the positive charge. Why is that? Yep, it's the more substituted one, and therefore the resulting carbocation is more stable. Sorry. So I'm gonna, in what color to use? Maybe green. There is the new bond that we made. Here is the old bond between carbons 1 of the orange subunit, I'm sorry, carbon 5 of the orange subunit and carbon 1 of the blue subunit. So we made the bond between 4 and 5. Conveniently, that makes a 6-membered ring. Taking these pi electrons, they are the ones that end up in this bond. And the positive charge ends up on carbon 2, where it's more stable because of hyperconjugation. All right. Now, I found that even though this reaction is fairly simple, the reaction looks like this. If you want to abbreviate it, the reaction looks like nucleophile attacks electrophile. But I found that students struggle anytime there's a ring involved. I think it creates this sort of instinctive panic sets in. And I don't know what it is. I don't know whether the hexagon is an innately scary structure for humans. Maybe it's because of honeycombs and we're scared of bees or something like that. I don't know. Maybe it should make us hungry. But whenever a reaction involves making a ring, the worry about the ring causes students to sometimes forget the principles that they know. This reaction is simple. It's just pi bond attacks electrophile to make a new sigma bond. The less substituted carbon gets the sigma bond so that the more substituted carbon has the positive charge. If you need to abbreviate things so that you can forget about the ring long enough to make the new bond, that's fine. Let's show you how you would do that here. There's a positive charge on orange carbon 2. And then there's a new bond between orange carbon 4 and blue carbon 5. You know that bond is there because we just drew an arrow indicating that that's the case. Once you've done that, then you can go back and remember that these two R groups were attached to each other and you made a ring. But you don't need to make it any more complicated than it is. All right, so pi bond attacks the nucleophile. I'm sorry, pi bond acts as a nucleophile to attack a carbocation. Another classic example of this is the reaction that generates Geranil Pyrophosphate to begin with. You have the pyrophosphate group leave from a simple precursor. And then you have this second isoprene unit, slightly different from the first. I'm sorry, I think I'm getting ahead of myself. So I think this is one isoprene unit, and it is one of the precursors to all terpene natural products in biology. This one has a name. It's called dimethyl allyl pyrophosphate. You don't need to remember that name. And it's great as an electrophile because of the pyrophosphate at an allyl carbon. The leaving group can leave to give you a resonance stabilized carbocation. Then you have this subunit, also a pyrophosphate, but it's an isomer. The double bond's in a different place. This is called Isopentinopyrophosphate. You don't need to know that name. But it also has a pi bond that can act as a nucleophile to attack, and carbon, we can form a new bond between blue carbon 1 and orange carbon 5. And the reason we do that is so that the positive charge that we form on breaking the pi bond ends up on the more substituted carbon. So in red is the new sigma bond that we made. Here is your orange isoprene unit. Here is the blue isoprene unit. The pi bond acts as the nucleophile. The positively charged carbocation acts as the electrophile. And just as we did before with alkenes acting as nucleophiles, we make the new bond with the less substituted carbon so that the more substituted carbon 2 can have the positive charge. All right? Different situations, exact same reaction. Question so far? Yeah. Yeah, so the question is, do we get rid of this carbon 2 carbocation to make geranil pyrophosphate? Exactly, and that's that's new reaction 3, E1 type elimination of beta protons. Let's see, I'm struggling to spell. E1 type elimination of protons beta to the carbocation. Yeah, so this is exactly how we get that geranil pyrophosphate. We just do an E1 type reaction, some base, we don't care what it is, probably a group from an enzyme removes that beta proton to give you the 10 carbon geranil pyrophosphate. And we can now look at that and we can try to tease out the reasons behind the observed double bond Regio selectivity. Notice I'm eliminating a beta proton from what I'm calling carbon 4. But there were also beta protons on carbons 1 and 3. So the question is, why do we preferentially eliminate from carbon 4? So let's look at the double bond. What kind of double bond would we have gotten if we eliminated from carbon 3? Right, the double bond would have been there, it would have been di-substituted. So that's not the most stable alkene. How about if we eliminated at carbon 1? Would still be tri-substituted, so maybe that's not such a bad idea. Can you think of a reason, though, why nature would like to have the double bond here between carbons 2 and 4 instead of between carbons 1 and 2? Go ahead. Is it because of the distance between where the pi bond is in the other isoprene unit in terms of thinking about future reactions like this one? Certainly. And the other reason is only if you have the double bond between 2 and 4 does this leaving group can the leaving group be at the allyl position where it can leave to generate a carbocation? It's only this regiochemistry, it's only having the double bond between 2 and 4 that makes it possible for this leaving group to leave so that we can do this next step. So this is a case where we're getting one of the two possibilities that's a more substituted alkene. And it would be difficult for us to predict that you should have the double bond between 2 and 4 versus between 1 and 2. And presumably there are other factors promoted by the enzyme or the situation that gives you this desired product. And this is our Geranil Pyrophosphate. So the reaction series we've just shown you, leaving group leaves, zooming out like crazy, leaving group leaves, pi bond attacks, carbocation, and then E1 type elimination. That can be used to tack on additional isoprene units. So we could do this series of reactions 1, 2, and 3 again to make a terpene with 3 isoprene units or 4 isoprene units. And you can start building up molecules with 20, 30 different carbons in them, and then start doing some of these other reactions where you make bonds that are not in the linear precursor, and you can develop some pretty complicated situations. All right, questions so far about the chemistry we're talking about? Because it's not in the text and you haven't had a lot of chance to read about it or any chance to read about it, I understand that it may be a little bit much. So don't let me move on if something's confusing. You don't have to just smile and nod because you want me to feel good about myself. I already feel great about myself, so I don't need any smiling and nodding. Go ahead. This is just, yeah, the question is, why did I draw limonene here? Did I even spell that right? I just wanted to show you the structure of limonene so you could see why we need to make this bond. Yeah. Based on what we've talked about, though, can you see a reaction that would allow us to get from this carbocation to limonene? What would you have to do? E1 type elimination, maybe remove that beta proton. Yeah, it's as simple as that. An E1 reaction gets you limonene. Okay, go ahead. Yeah. So, yeah, the question is, in the example I showed you, the leaving group left, and then in the reaction below, where then you use that positive charge as an electrophile, yes, the pi bond does attack at carbon 5 instead of at carbon 2, which shares the positive charge. Does it have to be that way? No. And in fact, there are situations where we attack the carbocation at carbon 2 instead of at carbon 5. So for a show all products question, would you need to consider that? The kinds of questions I ask about these molecules, because they're guided by biology, I don't really do predict products in that sense. What I would do is starting material, product, what was the mechanism, or I might ask you, hey, look at this fun natural product. Where are the isoprene units? And which bonds in it were in the linear Geranil pyrophosphate, and which did we make afterwards? Yeah, good. Go ahead. Right, yeah, so in limonene, why don't you create the double bond between 2 and 4? Wouldn't that be a more substituted alkene? The answer is yes. And why it doesn't do that, I don't know. You could argue that there might be some subtle conformational issues with the six-membered ring, where having 3 sp2 hybridized atoms in the six-membered ring might not be as favorable as having just 2. I'm making stuff up at this point, hand waving, but that's the other sort of punting the football answer is, well, the enzyme makes it that way. I don't like that answer because enzymes don't change thermodynamics, they just speed things up. So it's possible that this arrangement is more stable because of things that overcome the preference for a more substituted alkene. So it would not be a fair question for me to say, predict the product that forms from this, because there's multiple things you could draw. But it would be a fair question for me to say, here's this one and this one. What was the reaction that connected those two? Was there a reason we chose yellow 5 to go left versus right? It was really because of the only thing that distinguishes yellow 5 from blue 5 is the presence of this double bond. And that double bond indicates where the positive charge had to have been in order to do this reaction. So that was sort of why I drew it that way. I'm not sure that answered the question, but it's having the connectivity, the bond between yellow 5 and blue 1 be over here allows the double bond to be in the right place so that we can do that pi bond attacks electrophile reaction. There's been some questions in the E1 step. What is the base? This takes place in enzymes in aqueous environments. So you have functional groups on enzymes, like amino groups that can act as bases. Sometimes for carbocations, water is a good enough base to do the elimination. And there are actual kinetic experiments you can do to determine what the base is and which step it's involved in. I don't happen to know those details. And so I'm just hedging by saying it's some base, possibly from the enzyme, possibly from water. It's probably known, I just don't know it. And I guess I don't care enough to look it up. All right, other questions? All right, so let's talk about some more, some interesting things we can do from using these steps and using some of these intermediates. So let's copy this carbocation, or rather, since you guys don't generally have copy and paste capability, let's redraw the carbocation. Here's the double bond. Some of you may wonder from that step, why do we get the stereochemistry? I didn't show it, but why do we get the stereochemistry where carbon 2 is down relative to carbon 4, as in limonene? Presumably that is controlled by the chiral environment of the enzyme, favoring one enantiomer over the other. Oops, we wanted a carbocation here. And it'll help if we, again, highlight the 2 isoprene units, and it may help if we number things 3, 4, 5, 1, 2, 3, 4, and 5. Sometimes, by the way, carbons 1 and 3 are identical to each other, and that's okay. Here's a new bond we made, and then in another step, the bond between 4 and 5 is one that we made. Okay. So one of the things that can happen, in addition to elimination, I guess this is our 4th thing that can happen, is carbocation rearrangement. Can you still call it an isoprene unit if there's no double bond? Absolutely. If you've got the 5 carbons in this connectivity, even if there's no double bond present, you can call it an isoprene unit. So notice for this carbocation, you have a tertiary carbon adjacent to a tertiary carbocation. Now, I've not told you to worry about carbocation rearrangements in terms of a predictive sense in this case. Remember the classic example of a case where a carbocation rearrangement could occur was when you had a positive charge on a secondary carbon adjacent to a tertiary carbon. And then by moving a hydride over, you can interchange a less stable secondary carbocation for a more stable tertiary carbocation. Nevertheless, biology, this is the kind of thing I'd like you to be able to predict, but you should see how it would be possible to interchange one tertiary carbocation for another because they should be similar in stability. Again, to be clear, I'm not going to put you in a situation like this where you have 2 tertiary carbons and you have, a tertiary carbocation adjacent to a tertiary carbon, and then you have to worry about whether or not a rearrangement would occur. Not going to do that in predict the products questions. But this can happen for terpenes, and it happens because it results in a carbocation that can lead to other desired products. So a 1,2 hydride shift would involve this hydrogen leaning over to make a bridged carbonium ion where the hydrogen is shared evenly between carbons 4 and 2, and then leaning over enough such that we actually make a new bond with carbon 2 instead of with carbon 4. So we call that carbocation rearrangement. Another word for it is a 1,2 hydride shift. And that puts the positive charge here in the ring. And then that generates a new tertiary carbocation. Why would we do that? Again, because that can lead to other desired products. Okay. Question so far? Yeah. No, will it only move from tertiary to tertiary if it's in a ring? No, I don't think that's a defining feature. The reason the carbocation rearrangement happens is because, well, imagine you're on a potential energy surface and you have one tertiary carbocation. The barrier to changing from one tertiary carbocation to another is probably pretty low. And the equilibrium constant, because they're similar in energy, the equilibrium constant should be close to 1. And so what this means is it can happen and you can go back and forth from one to the other. Why would the pathway occur? Well, why do these natural products form in the first place? And the answer is they give some selective advantage to the organism that makes them. Sometimes it's not at all clear what that selective advantage is, but the key issue for terpene chemistry, as far as we're going to talk about it, is not can you predict what would happen, but can you explain what happened given starting material in a product? In other words, if I showed you these two, would you be able to see that, oh, it's a carbocation rearrangement that gets me from here to here? All right. Go ahead. Which one and where? I'm sorry. Yeah. Yes. Yeah. You could do that. That would generate, that would be weird though. It would generate a 3-membered ring. And the other thing to remember is that the positive charge on carbon 5 is not on carbon 5. This is actually a 3-pi system. It's an allyl carbocation. It's resonance stabilized, so the positive charge is simultaneously on carbons 2 and 5. And because of that, no, and these pi electrons are not just between 2 and 4, they're also shared between 4 and 5. So that kind of thing wouldn't happen. Okay. So I want to show you some interesting products that can come from these 2 different carbocations, right? You have the one where the positive charge is outside the ring, and you have another where the positive charge is inside the ring. So let's draw again the one where the positive charge is outside the ring. And it still may be useful to draw the isoprene units and remind ourselves of which bonds we've had to form so far. All right, this is a case where you have a tertiary carbocation, which could be an electrophile, and it's in the same molecule as a carbon-carbon pi bond, which could be the nucleophile. So you're going to love this. Imagine the pi electrons reaching down on the bottom face of this molecule and attacking the positive charge. Dun, dun, dun. Do you hate it yet? You might. So let's just think of this in terms of a typical addition to an alkene reaction. When an alkene attacks an electrophile, we make the new bond with the less substituted carbon of the alkene so that the more substituted carbon can have the positive charge, right? So that means our new bond, a new sigma bond, we're going to form between blue carbon 4 and orange carbon 2. Everything else is going to stay the same. And then where's my positive charge going to end up? On blue 2. Okay. So if we want to, we can actually draw that outcome. And sometimes it's okay to do this with really, really long bonds so you can at least get the connectivity right. And then you can worry about the actual shape of the molecule later. So here's orange 2. And we made a new bond with blue 4. I'm going to draw that in red. Oops, terrible, huh? Stretching, okay. So now those 2 are bonded together. And we've got a positive charge on blue 2. A more realistic picture of what this looks like is that you have the positive charge here, and then you have orange 2 below the ring and bonded to orange 4 and blue 4. And that is where we're going to have to leave it today. But for next time, I want you to work through this example until the connectivity of the molecule makes sense. And I'm highlighting in red all of the new bonds that we've made. And I'll number the carbons of the isoprene unit here.